Greetings, Professor, and greetings to everyone. I'm Somnath Reddy Galapati, and today I'm presenting my project report on optimizing machine learning models for house price prediction and construction planning for the course requirement of CNST 6308 Data Analysis in Construction Management. So, coming to the introduction, the house price prediction significantly impacts buyers, sellers, investors, and construction managers. So this study approaches multi-phased house price prediction through exploratory data analysis and also predictive modeling methods. So it includes the traditional linear regression and also the four different advanced machine learning tools like gradient boosting, random forest, LGBM regressor, XGBoost. So the advances in data volume and compute tools have driven the adoption of predictive modeling. So the exploratory data analysis uncovers linear relationships and correlations to identify key determinants of house prices. And the machine learning algorithms, as I have mentioned, the traditional one is linear regression, and the advanced ones are random forest, gradient boosting, XGBoost, and light GBM. So the objectives here are to understand the set's main characteristics, compare regression models to determine best algorithm to predict the house prices for a separate location, which I have took is like the USA housing from the Kaggle, and also engage data splitting process, feature engineering, and model fine tuning meant to optimize the predictive performance of specific algorithms. So the data set includes the dependent target variable as the house price and the independent variables as average area income, average area houses, average area number of rooms, average area number of bedrooms, average population, and the address. So this is my literature review one. Here are the key points. So the basic objective was the machine learning model for house prediction using feature like location, room count, and economic factors, where this one links with my data set. And they use the methodology includes the data collection, cleaning, feature engineering, and splitting data sets into training 80% and testing 20%. And handling missing values improved these model performance in this literature. And the second one, they just use the fine tuning, k-fold cross validation, and outlier removal to enhance model efficiency and reliability. And this study was done by Aditi Sahasan et al. And their objective was to learn the algorithms for real estate price prediction using features like size, locality, and home specifications, just as same as the dataset that I have chosen. And this application involves the insights for buyers, investors, and developers, simplifying decision in the real estate market, and also especially for the construction planning for a specific location or the project site to take up for the residential construction planning for any construction company. So this way, using this application, the construction managers could do very good construction planning, and they can estimate how the company goes into profit or loss taking up in project by this analysis and all. And the third literature review, they just use the gradient boosting, leveraging random search for hyperparameter tuning. I just took this literature review paper for the gradient boosting analysis, how they just used, and also they just use light GBM, XGBoost, and random forest for RSME performance and squared R value performance and all. So coming to the methodology that I have used, first I did the data pre-processing. The first step in it is cleaning. So the data cleaning is very important for any statistical analysis for to explore the data. So I do have one in the data as address. So address typically it doesn't give any statistical value or a numeric value to make an analysis with the dependent variable of price that I have chosen, and also this one, the address has independent variable. We cannot make any scatter plot or any graph, any histogram. So this way we can just clean up all the unnecessary data which doesn't help out for the statistical analysis. The next is missing value handling. Since it's a very large data set, so there may be some of the missing values due to the survey that was done or collection of data time it may have missed. So by this handling missing values, I just use the data in null function to check how many missing values are there, and I found average area house age have six missing values, and I just used it for next processing. And I just did scaling and also the splitting. The scaling is done by the standard scaler to transform the data to have mean zero and standard deviation of one. So, and the linear regression and gradient boosting, both of them models are sensitive to feature scaling. And the data, I just trained it as 80% and I just tested it as 20% by the data split function and all. Then the first model, the linear regression, it shows like very positive correlations between price and average area income, and the price and average area number of rooms versus the price. Both of them have shown the very good positive correlations, and it is tending, it's like positive right skewed, so it's tending to 1, so they both have a good correlation. And the next one, the correlation value of 0.64 conclude that there is a positive correlation between price and average area income, and the correlation value of 0.33, which is typically less, but still it shows like a V2 moderate positive linear correlation between price and average area houses. But as that of the analysis, as we move further, average area number of bedrooms versus price does not have any good positive correlation as previous four independent variables, and this shown a value of 0.17, which is very weak. And also if you see the graph that I've presented on the slide, it doesn't show any good positive like the linear correlation between them. So I just transform the these equations into like trying of the cube, trying of the square, and trying of the logarithmic, but I still find nothing from them, and I just removed out the data from my data set for the further analysis since it's not linear. So for the linear regression, again I just made a scatter plot, and the plot for all the different variables like the price and other independent variables and all the independent variables. It's like most of the all the combinations that we work out on these independent variables, and we see that the every scatter plot shows like a positive relation, and overall all the distributions show a like a moderate to good positive correlation between the variables and all. So this is like the actual and predicted house prices I just made from the linear regression using Python code, and we can see that's a very good positive correlation, and it showed a value of 0.9, which is typically like if it is more precise we can just even write it as 1. So this has a very good positive correlation in the linear regression for the specific data set I have chosen. For the random forest, this it is just the same. It's 0.86. The scatter plot shows the positive correlation between them. And also I just calculated the evaluation metric values for MAE, MAC, and the squared R value. And coming to the gradient boosting machine learning model ensemble a weak prediction models for the decision trees in a sequential manner to minimize errors. And the gradient boosting corrects the previous three errors that was made by random forest regression model. And the gradient boosting I just evaluated further for the evaluation metric values, and I just use for the comparative analysis in the next upcoming slides. So XGBoost and LGBM regression, both I just used. Both the algorithms are basically designed for performance and speed. So these two models outperform linear regression and random forest by virtue of their ability to model complex non-linear relationships within the data, if there are any such, just as the bedroom number of bedrooms and the price example that I have chosen. This may be a future scope for this project, or this data can be used to this regression models can use to check what regression like what relation they do have between them for efficient modeling. And also I just calculate the evaluation metrics, and this is the summary of all the evaluation metric values that I have got. And we see that the linear regression have the highest R square value, which was a positive correlation, followed by gradient boosting, XGBoost, and light GBM, and then followed by the random forest. So analysis using mean absolute error evaluation metrics. The fact that the MAE of linear regression is the least means that it's outsized by any other model in this comparison. It can be said that models of random forest and gradient boosting have comparable MAE values that are a bit higher than the linear regression. Essentially, this analysis shows and finds that the linear regression to be moderate and a good choice for this regression analysis for the specific this data set of the USA housing and all. And then as we move on for the mean squared error, it also just show that the analysis show the lowest value for the linear regression there. And essentially this analysis show that the linear regression is to be the best model that we can choose for the this specific relation regression problem. Coming to the R square value, typically we can just by viewing the graph, we can just see that the linear regression has 0.9 as a typical value, which is very, very nearer to 1. And we can just simply say that the linear regression model would be the best suit for this specific data set. And these are the some of the conclusions that I have drawn. This suggests that the linear regression model is more reliable and credible because of the 80-20 data split for the train and test. And Overall effectiveness performance measurement of the model was based on testing set will include accuracy precision. And the tests are meant to provide comprehensive insights into how useful the model could be in predicting house prices. This research has also shown that the linear regression is a reliable baseline for house price prediction in structured datasets having linear patterns. For capturing non-linear relationships, XGBoost and gradient boosting provide robust alternatives. This is the future scope, fine-tuning models like random forest and gradient boosting, integrating the best performing model into a real-world application. Since like the construction planning is a very first stage that we take up when we are doing a specific project, we just analyze the previous projects. So, uh, just moving on for the different linear regression models like machine learning models to check how effectively a model is working for the specific data set, and we can just use that model. And thank you.